section 1.2 proposition, 명제. A sentence is either true or false, not both. It's called a proposition. If you have a sentence which is either true or false, okay, then we call it is a proposition. And this notation means conjunction of P and Q, and this notation is called P and Q. Okay, conjunction of P and Q. P or Q is a disjunction of P and Q, and we read it as P or Q. Okay. So if P is a sentence, P is a proposition, it is raining, and Q is a proposition, it is cold, then the conjunction of P and Q is this, P and Q. So it is raining and it is cold. Okay, disjunction of P and Q is it is raining or it is cold. Okay, this is truth table that you already knows well. Okay, the conjunction of P and Q, truth table of conjunction of P and Q is this, T, F, F, F. If one is false, then if one of these P or Q is false, then the conjunction is false. For disjunction, this is for disjunction. If the disjunction of P and Q has a truth table, which is TTF, TTTF, which means if one of P or Q is true, then the disjunction is true. And it's only false when both P and Q are false. So P or Q is inclusive or of P and Q. Okay, so if P and Q are both false, then conjunction of P and Q is false, but otherwise it's all true. Here, so P is the millennium is 100 years. That's the sentence P, proposition P, and Q. The proposition Q is a millennium is 1,000 years. Yes, here P is false and Q is true. So disjunction P or Q is a millennium is 100 years or millennium is 1,000 years. So this sentence is true. Okay, so it is a proposition. Negation, negative, is denoted as this, not P. We call it not P. Okay, not P. Which means it is not the case that P. Okay. Truth table is this. If P is T, then not P is F. Then truth table of if P is F, then not P is true. Negation is simple. So like if the sentence P is Paris is the capital of England, then not P means the Paris is not the capital of England. And here this is important. Operation precedence. This is the order. When you have these notations, not and or, then the order is this. The order of operation is not is first, and is next, and the or is the last. And also when you have the operations, then multiplication first, and division is next, and addition is the next, and negative subtraction is the last. So when you have a set of equations, when you have equation including lots of these notations and symbols, then you already know it has the order of operations. Okay? So you don't have to make a lot of parentheses if you know this order. 무슨 말인지 알죠? 이렇게 수식이 쭉 있을 때 다 가로가 많이 없어도 그게 값이 뭔지 다 어그리하죠. 그것은 이 순서를 따르기 때문에 그런 거예요. 특히 컴퓨터에서 코딩하고 할 때 이 순서 할 때마다 가로를 주지 않아도 되는 게 이미 순서를 정해놨기 때문이에요. Okay? So we have the order. This is fixed, so it won't be confused at all since now. Okay, proposition P is false and proposition Q is true and proposition R is false. If it is given, then determine whether the proposition this is true or false. How? So since we know the order of operations, so negation first. So we have this. Okay. So if P is false, then not P is true. Okay, not P is true. Next, this AND is first, AND is the next. So Q and R. You see, Q is true and R is false. So this is going to be false. Now we have true and false. So true or false. So this gives, since not P is true and Q or R is false, like Q and R is false, so true or false statement should be true, like what you see here. This comes from the truth table. This comes from here, and this comes from here. This is what? This is true, and this is false. So truth table gives you, TF gives you, this disjunction should have T. So this is a true statement from the given. Okay. Okay. Next, conditional proposition and logical equivalence. 이제 이건 동치인 statement에 대한 얘기예요. Equivalent, logically equivalent statement. Conditional proposition. Okay. If P then Q. This is a conditional proposition. If T is true, then Q follows. So there is a condition here. So we call it is a conditional proposition. P implies Q. Okay. This can be written in this. These are all logically equivalent here. P implies Q. This is same as so not this and not P or Q. And these are all same. Yeah. Here, we call this P is a hypothesis, 가설, and Q is a conclusion. If P is a condition, and that's the conclusion. Okay. Hypothesis and conclusion. If P is Q, then this is a hypothesis, and this is a conclusion. 가정이 주어지고, 가설이 주어지고, 그 다음에 이걸 가설이라고 하고 이걸 결론이라고 하는 거예요. 이 P. So these are equivalent statements. You can easily check. Here is an example. If the P statement P says the math department gets an additional $60,000, Q sentence tells that the mathematics department will hire one new faculty members. So P implies Q. If P, then Q. And this means if the hypothesis is if the math department get an additional $6,000, then math department will hire one new faculty member. So this is hypothesis and conclusions. If money is given, then we will buy something. Here is a truth table. Because they are equivalent because of this truth table here. P implies Q has TFT T, like this. But here, not negation of P and not Q, it has same as TFTT. This, as you this, if those sentence has the same truth table, then we call these two sentences are equivalent. Two propositions are equivalent. Okay, so this is a way to show two propositions whether equivalent or not by making truth table of those two propositions. Here, next. Okay, here, this is an example, truth table. These four propositions are all, okay, find the, okay, suppose P is true and Q is false and R is true, then find the truth value of each propositions. Let's try to find the truth value of the first one here. If P is true and Q is false, then P and Q is false. And R is true. So now what we have is P and Q is false and R is true. So P and Q implies R. So what it is? So what it is? Okay, here. If this is false and true, then if assumption is false, if hypothesis is false, then whether the conclusion is true or false, the sentence should be true. So like, if you give me money, then I will do something. But if he don't give the money to me, then whether I do the work or not do the work, they are all okay, isn't it? 조건과 this all comes from the truth table. So if a hypothesis is false, then whether the conclusion is true or false, the whole statement should be true. So this is the truth table of it. So this is truth value. The truth value of this sentence is true. Next, here, if P is true and Q is false and R is true, then Q is false and R is true, then this is the true statement. P is a true statement. Then true implies true, then means true and true. So the truth table should be true, isn't it? P is true and Q implies R is true, so this is true. So this all comes from the truth table that we have since. So one thing that I give an emphasis is this. Truth by default or viciously true. This means if the hypothesis is false, then it is always true. 항진. 언제나 true in statement. Here, the hypothesis is false, then where the conditional proposition is always true. 항진. Always true. Proposition is like what I mentioned. This is what I mentioned. Here, if P implies Q. If a hypothesis is false, then whether the conclusion is true or false, the statement is always true. This is 항진명제. So in English, we say it's true by default or viciously true. That's what we say. This is also quite important. So when you make an algorithm, if the assumption is false, then you don't expect anything. It's always true. So it's very important that we start from the right statement, right hypothesis. Okay. Next example shows find the truth value of the original proposition, and this converts in this case. If Jerry receives a scholarship, then he will go to the college. He will go to college. Okay. Right and is converse simply in your word. Okay, so if P, the hypothesis is Jerry receives a scholarship, and conclusion is Jerry go to college. Okay, so converse is this. Jerry receives a scholarship, but he don't go to college. Okay, converse is this. Jerry goes to college and he receives a scholarship. Just converse, just reverse it, just change this order from P to Q instead of the converse is P. Q implies P. So Jerry goes to college, then Jerry receives a scholarship. That's the converse. Okay, next, find the truth table, truth value of its converse. Okay, hypothesis Q is true and the conclusion P is false, then converse is false. And if hypothesis is false, then conditional proposition is always true. So here, like this. 그러니까 여기서 가설, 만약에 제리가 스칼라십을 못 받으면 그러면 제리가 대학을 가건 안 가건 그 스테이트먼트는 always true고, 그리고 여기서 만약에 하이퍼스 Q가 true이고 conclusion이 P가 false이면 이 경우에 자, 즉 제리가 대학은 갔는데 근데 제리가 장학금은 받지 않았다. 그러면 장학금을 받지 않았다. 그러면 이제 그렇다 그러면 converse는 그 converse는 이제 false가 된다는 소리죠. 자, 어쨌든 P를 if we define P as Jerry receives a scholarship and Q, we define Q sentence Q as Jerry goes to college, then this conditional proposition can be written P implies Q, and the converse of this proposition is Q implies P, and the truth table of this is depend on whether the given condition is true or not. So the truth table is depend on whether P is true or Q is true. So on each case we can draw the symbolic these propositions whether it is true or not. And the next thing is the if and only if statement. If and only if statement. This proposition is true when P and Q have the same truth values. Like here, P implies this conditional proposition is on both sides, so we call it is a biconditional proposition. Okay. P implies Q and Q implies P. So this also can be written as this: P implies Q and Q implies P. They are equivalent. Why? These two truth tables are same. So they are logically equivalent. Okay. And the earlier examples it explains some of this concept. Here. As you see, the truth table is this for this biconditional proposition, and also the truth table of this proposition can be written as this, which is same as this. So these two statements, these two propositions are logically equivalent. In this case, we use this notation, and also we write it, sometimes we write it as a if and only if. Abbreviation of if and only if is IFF, if and only if. So when you see this, that means biconditional propositions. Okay. This is one simple example. Yeah. If we define P is 1 is less than 5 and Q is the 2 less than 8, then if P and Q are true, then proposition by conditional proposition P if and only if Q is true. If P is if these both of the statements are true, then clearly this satisfies. Here, so yeah, here. So here, yes, now we give a rigorous definition of logically equivalent. Proposition P and Q are made of the proposition PI's, and P, Q are called logically equivalent if the given any truth value of PI's, either P and Q are both true or P and Q are both false, then we call these P and Q are logically equivalent propositions, like this. These three are all logically equivalent because they have same truth values. With this concept, we can define De Morgan's law for logic. De Morgan's law for logic. This is it. Negation of P or Q is equivalent to negation of P and negation of Q. Here is the proof. Find out the truth value of the left-hand side and find out the truth value of left-hand side. As you see, they are same, so we can tell they are logically equivalent. Also, this P implies Q is the negation of P implies Q is logically equivalent to P and not Q. Okay? Because the logical truth values are same. The same thing, the one more thing is here. Negation of P implies Q is logically equivalent to P and not Q. Okay. With all this, we can, and also this contrapositive. This is also important. Contrapositive. 이게 대우라고 하는데요. Contrapositive. P implies Q. The contrapositive of P implies Q is not Q implies not P. They are also logically equivalent. Because the truth tables are same. So with all this, with these properties, then now we can handle the symbolic propositions with these rules. Then we can replace, when we wanted to show something, instead of showing that given statement is true or not, we show the equivalent logical statement is whether it is true or not. So we can choose the easier proposition to get an answer. 자, 지금 보면은 여러 가지 이 성질들이 있었죠. 그 여러 가지 logically equivalent한 그 성질들을 봤죠. P, Q를 에다 negation 할 때는 P는 그대로 두고 and하고 not Q로 한 것을 보여도 된다는 거고, P이면 Q이다는 스테이트먼트를 보이기 위해서는 Q가 아니면 P가 아니다는 스테이트먼트를 보이기만 해도 똑같다는 것을 보이는 그런 셈이거든요. 그러니까 위에 있는 이런 조건들을, 이런 성질들을 이용해서 뭐뭐이면 뭐뭐다는 걸 보일 때 다양하게, 또는 뭐뭐이면 뭐뭐가 아니다는 걸 보일 때 그 보이기 쉬운 equivalent statement를 이용해서 보인다는 거예요. 그 중에서 가장 많이 쓰이는 게 이거예요. 이 contrapositive, 대우를 이용한 증명. P면 Q라는 걸 보일 때 바로 보이는 것보다는 Q, 그렇다 그러면 Q가 아니라 그러면 P가 P일 수가 없다. P가 아니라는 걸 보여서 증명하는 것이 이제 아주 티피컬한 증명 방법이에요. Okay, so we use those properties in the next chapters. In chapter 2, proof. Okay, here's an example of contrapositive. If the network is down, then they cannot access internet. Write this conditional proposition symbolically and write the contrapositive and the converse symbolically and in word. So let P, the first statement, P, conditional state proposition, the network is down, then Q, let's say QB, they cannot access the internet. So P implies Q is this given conditional proposition. The contrapositive is not Q implies not P, which means if they can access. Here cannot, so negation is can. So if they can access the internet, then network is not down. That's the right statement. Okay. So that's the contrapositive of the given statement. P implies Q, then not Q implies not P. They are logically equivalent, as you see. Actually, this is a proof. With those, we do the we start section 1.4, argument and rule of inference. Okay, argument and truth. Here, we cover the process of drawing a conclusion from a sequence of proposition, which is called the deductive reasoning. It's deductive reasoning is in our word is 연역적 추론. So one example of this is 3단 논법 that you have learned. So we and the deductive reasoning is the process of reasoning from hypothesis to reach a conclusion. So from the given hypothesis, with the logical argument, we reach the conclusion. That is called the deductive reasoning. Okay, given proposition are called the hypothesis or premises. So given proposition is called the hypothesis, and proposition that follows from the hypothesis are the conclusion. So from the hypothesis with the logical argument, if we reach the sentence, then that is the conclusion. So a deductive argument consists of hypothesis together with a conclusion. A deductive argument all together consists of hypothesis together with the conclusion. So any deductive argument from this, if P1 and P2 Pn, then Q. With this hypothesis, we reach the conclusion Q. Here, the argument is valid if the conclusion follows from the hypothesis. Okay. If we used only the hypothesis to reach the conclusion, then we call it the whole argument is valid. Okay. Which means if all PI's are true, then Q is true. Then this argument is the whole argument to reach that conclusion is valid. We write all this in this notation. P1, P2, and Pn's are all true, then we reach it. Therefore, Q was reached. This is the conclusion. Since it is hard to type, so and also it takes more space, So we can simply write in this one line. Instead of many lines, we just use one line to write symbolically this sequence of propositions. Here the symbol, this symbol means therefore. So these propositions are called hypothesis, and this last proposition is called the conclusion, which draws from the given hypothesis. The argument is valid if these are all true and Q is also true. Otherwise, the argument is invalid, or fallacy, 오류가 있다. We should use those. Then, what is the rule of inference thesis? That's the valid argument are used in a larger argument. Here in larger argument, I will explain more. Here. Example 1.42 here. Modus ponens. So modus ponens rule of inference or law of detachment. We call it 이걸 긍정 논법이라고 그러는데 determine whether the argument this is valid. Let's determine it. P implies Q and P, and therefore Q. So in order to show it's valid, we write P implies Q is a true value, and if P is true, then Q is true. So as you see here, so if the first proposition is true and second proposition is true, so if those conditional propositions both are true, then conclusion is true. So this argument should be true. Okay, valid. Okay, here is the explanation. By the truth table, if hypothesis this and this are true, then conclusion is true. So argument is valid. You can easily see from the table. Second solution. Using the truth table by direct verifying, the hypotheses are true, the conclusion is true, like you see. If P implies Q and P is true, then Q is true. Otherwise, P implies Q would be false. 이게 무슨 말이냐면 만약 P implies Q가 true이고 P가 true인데 Q가 true가 아니라고 가정한다 그러면 P면 Q가 돼야 되고 P가 true이면 당연히 P가 true이면 Q도 true여야 되는데 Q를 true가 아니라고 가정한다면 그러면은 P가 true란 말에 그 모순이 생기는 게 되죠. 따라서 그런 일은 벌어질 수 없다. 이렇게 증명할 수도 있다는 거예요. 이렇게. So if you assume P this is true and this is true, but the conclusion is false, then it occurs a contradiction. So this assumption this assumption Q is false occurs a contradiction. So it is so this argument is valid. So this is the kind of reasoning that we write. As you see here, this is very clear. But when you use the word, sometimes it is more vague. It takes more confusion. Could. So now it's time to think a simplified and clear way that to make our argument valid. That's the reason that we learn the method of proof in chapter 2. Okay, here is the summary of what we have covered. Here, P implies Q, and if this is true and this is true, then Q is true. Then this rule is called the modulus ponens, which is called the 긍정 논법. And this, if P implies Q and not Q, then not P. This implies this. This is called modulus tollens, 부정논법. 이게 말하자면 이제 모순을 이제 유도하는 가정을 부인하고, 그러니까 결론을 부인해서 이제 가정이 틀렸다는 모순을 유도하는 이제 모순을 이용한 증명을 할 때 쓰는 부정 문법입니다. Modulus tollens. And addition and P implies P or Q. It's clearly it's always true. It's just adding the condition. P and Q, then clearly P is true. If P and Q is true, then which means P is true and Q is true. So P should be true. So this is a simplification. So as you see here, if you if you have same, you can simplify this, and you and also there are, and so yeah, with this we can utilize this different type of rule of inference when you proceed our argument. And this is called hypothetical syllogism, which is the 3단 논법. P implies Q and Q implies R. Then P should implies R. This is called the 3단 논법. In English, hypothetical syllogism. Okay. And disjunctive syllogism is P and Q and not P implies Q, and that is called disjunctive 3단 논법. Okay, then how do we use this? Let's see some examples. This is an example of hypothetical syllogism, 3단 논법. Okay, which rule of inference is used in the following argument? If the computer has 1 gigabyte of memory, the big memory, then it can run fast. If the computer can run fast, then the sound should be impressive. Okay, so therefore, if the computer has 1 gigabyte of memory, then sonic will be impressive. If computer has a good performance, then sound should be good. So here, if we write it in the symbolically, then the first proposition is P is the computer has 1 gigabyte of memory, and the second proposition Q is the computer can run faster. Proposition R is the sonic will be impressive. Here, the argument can be written as P implies Q and Q implies R. So P should implies R. This is the example of hypothetical syllogism. 3단 논법. The fallacy of affirming the conclusion. Here, if 2 is equal to 3, then I ate my hat. I ate my hat. So 2 is equal to 3. Is this statement is true or false? Mr. 문계정. This is a typical example of a fallacy. Okay, if this argument is valid, if P implies Q is true and Q is equal to true, then P should be true. But let's see. This is also possible if P is false and Q is true. Even though 2 is not equal to 3, I still can eat my hat. So in this case, P is not true, thus the argument is invalid. This fallacy is the fallacy of affirming the conclusion. So when you do make coding, then you should be very careful to be followed in this case of fallacy. Represented the next example shows this. Represent the argument. The bug is either in module 17 or in module 81. Then the bug is a numerical error. So module 81 has no numerical error. And therefore, the bug is in module 17. This argument given at the beginning of this section symbolically and show that is valid, so that it is valid. Okay. Actually, this was one example which was given in before, and now show it is valid. Let's see. Make it make this P the first state, the first proposition as P, and second Q, and third R. So P, Q, R. We have these three propositions. So we can rewrite it this way. Okay, here, in symbolically, bug is a numerical error. Okay, modulus 81 has no numerical error. So this is a sentence that we had. This is propositions that we had. P, the first, bug is either modulus 17 and 81. So P or Q is the first sentence. Next, bug is a numerical error, so that's R. Next, modulus 81 has no numerical error. Bug is in 81. So this can be written 81 is a numerical error. That can be written as the first third sentence is okay. This 81 has no numerical. That can be written R implies not Q. R implies not Q. That's what we have. Okay, so this is the symbolic representation of those three propositions. And then conclusion is bug is in module 17. That's P. So let's check these propositions using modulus ponens. From R implies not Q. We assume these three propositions are true. Okay, and conclude. Let's conclude. From those R implies not Q, and R to conclude not Q using the distinctive syllogism P and Q and not Q to conclude P clearly. Yeah. Okay. The conclude P follows from the hypothesis. 이게 무슨 말이냐면 R이면 not Q인데 R이 true라 그러면 당연히 not Q가 따라오게 되겠죠. 오케이. 그다음 P와 P이거나 Q인데 P와 Q인데 not Q이면 그건 상관없이 P이거나 Q인데 Q가 Q이거나 not Q인 거는 P가 true인 건 상관이 없는 거거든요. P가 true이고 또 Q가 true인 것 둘 중에 하나만 true이면 전체가 true이니까. 그러니까 the P follows from this. So P follows from these hypotheses. That means P is valid. So all argument is valid. That's what it says. Here what? So with this, if these three propositions are all true, then we have the bug is in module 17. Okay. This is what this example wanted to show. Okay. 자, 이런 것들을 이제 이런 것들 버그가 어디에 있는지를 찾는데 이렇게 복잡한 상황들이 여러 개가 있을 때 그런 것들을 이걸 말로 해서 하다 보면 혼돈이 자꾸 일어날 수 있으니까 로지컬 심벌리컬리 바꿔놓고 그리고 규칙에 따라서 적용해서 그래서 그 버그가 어디 있는지를 그렇게 누가 거기에 있을 것 같다고 이제 지적한 것이 맞는 말인지 틀린 말인지를 이제 확인할 때 이런 식으로 심볼릭 이런 아규먼트를 사용하는 것이 효과적이다는 얘기예요. So, yeah, this kind of techniques will be needed to check Next example, 1.4.6 says the argument P is the San Diego Chargers get a good linebacker, and Q means the Chargers to beat the Denver Broncos, and R state argument says the Chargers can beat the New York Jets, and argument S says the San Diego Chargers can beat the Miami Dolphins. Then if we write it in symbolically, then P implies Q, and Q implies R, then B, and Q implies S. If these are all three, then the conclusion is P. Let's check whether this whole argument is true. Here, symbolic. So the so P. So if they are all true, then if P implies Q, Q implies R, then that means P implies R. We have this proposition, and then when this is true and assume P is true, then using modulus ponenus to conclude the R. So clearly, if P implies R is true and P is true, then clearly, since P is true, R is true. So we have R. Also, P implies Q and Q implies S, then using hypothetical symbolism to conclude P implies S, clearly. So we have all this and this and this. And also from here, to also we have the S as well. Then R and S are both true, so we have R and S is true as well. So the argument R and S, which means the San Diego Chargers can beat the New York Jets, and the Chargers can beat the Miami Dolphins, are still true. So this conclude this conclusion that follows from the hypothesis. So it's a conclusion. Yeah. Okay. So what this means is, 만약에 이제 샌디에고 차저스가 이걸 다 비팅했다고 한다면, 그러면 굿 라인베커를 이제 확보했다는 이제 그런 그 아규먼트, 그런 하이포시시스가 true일 거라는 이제 그런 결론에 도달할 수 있다 하는 그런 예를 보여주는 example이었습니다. Next section is a quantifier, and the last section 1.6 is a nested quantifier. That's the end of section chapter 1. Since the time's up, so we'll take a 10 minutes break to conclude the chapter 1. Any questions before we finish up chapter 1?